So let's review some alkene reactions here. I'm going to go ahead and start off with a generic asymmetric alkene. When I say the alkene is asymmetric, it's just that it's different on both sides. All right, we had a bunch of reactions here that we went through. So what I want to do here is I'm going to go ahead and draw the product here, and I want you guys to help me with what reagent did that. See if you guys remember these. All right, let's just go upward here. And let's say this first one is going to get rid of the double bond. Yeah, so it was H2. Is it PT or PD? PT. Or the nickel? Oh, nickel. So it works out where you can use nickel, palladium, or platinum. If you look at the periodic table, they're all in the same column. They have the same chemistry. What is the one that's most commonly used, though? It was palladium is the common one. So I do want to mention here that the catalyst here is nickel. And I put the little 0 there to imply that it's the metal, not the ion. It's nickel, palladium, or platinum. So the main one here is palladium, is the main one that you want to use. There is a distinction between like how good the reaction works and the cost. So platinum actually works very well for this reaction, but it's super expensive. And then nickel doesn't work so well, but it's cheap. So the middle ground here is palladium. It's a cost issue for the most part.
What if you only put H2 in palladium? Is that wrong?
Well, it should be like nickel on carbon, right? So if you don't put the on carbon part in there, I'm not worried about it. Yeah, so basically if you want to be totally correct here, you should write it as palladium on carbon like that. What was the name of this reaction? Hydrogenation. And another thing here is it syn or anti-addition? Syn addition. What does that mean again? Yep, they add on the same side. So I'm just going to emphasize that by drawing H's pointing in the same direction. So that. Do you guys remember the common industrial application of hydrogenation we talked about last semester? It's typically a way to get rid of unsaturated fats. So if you have an unsaturated fat, that means that it has an alkene in it. They can get rid of it by hydrogenating it. I think the common application of this is hydrogenated vegetable oil. They basically do this reaction with it. All right. So the other thing we could do here is add some bromines to it. And I'm showing you the stereochemistry here. This is an anti-addition. What reagent does that? Yeah, this is Br2. All right. So the name of this reaction was the bromination. The alternative was the chlorination as well. But honestly, this bromination is the more common one here. The main reason why bromination is more common than chlorination is because of how you actually have this element in the lab. Bromine, Br2, is a liquid at room temperature where chlorine is a gas. So it's easier to work with. All right, so bromination is an anti-addition. We're going to come back to that reaction later. All right, so what if we have Br2 and water? What is different about it? You get a Br and an OH, and where does the OH go? More substituted. All right, so I'm going to go ahead and show the OH more substituted. Okay, and then I did show you guys a way to go from this compound to a diol that. And this was an anti-addition. Does anybody remember the reagents for that? That would be an alternate way to start. That would work for if you, basically from here to that. It was excess hydroxide. Don't worry about this reaction too much. We are actually going to cover this next chapter. This is an epoxide reaction. It's part of the first chapter. But for those that have me for 241, I typically show this reaction in that section because it's relevant. So that's how we get an anti-addition. So the other way that we talked about at making diols was via a syn addition. There were two ways for this. So let's go ahead and show the syn addition product here. So OH is pointing in the same direction. The first one, I believe, was KMNO4, and the temperature needed to be specific here. With a hot or cold? Cold, yes. So cold. And what was the other way to do this? This was the osmium tetroxide reaction. It's OSO4. So OSO4. Typically people will detail a workup with it too. I'm not worried about the workup step. Just as long as you remember the osmium, then you're probably good. I believe it was a bisulfate workup. Not that important here. All right, what happens if we have KMNO4 and it's hot? So here I'm going to say KMNO4 hot. Yep, this is oxidative cleavage. So here we're going to get that. And what is my other product? What was that? Carbon dioxide. Yep. Typically it works out where you're going to trade a double bond to C, trade it for a double bond to O. It works out though where if the carbon's at the end of the chain, it'll fully oxidize into CO2. So that is, this is oxidative cleavage here. So go back to here for a second. This was syn addition for the diols. This was oxidative cleavage. Okay. What was the other way for oxidative cleavage? What was the alternate? It was the better way to do oxidative cleavage. It was the ozone reaction, right? So here, I'm going to add a little bit to it from what I showed you guys last semester. But the first step is ozone. I don't think I showed the intermediate last semester, but I have it here in my notes anyway. So you get a really weird intermediate here. So essentially the oxygens get plugged into the double bond. Like that. And then how you do the workup step governs how oxidized your product is. So I had three versions that we went through last semester with this. Okay, so in most textbooks, their second step will be dimethyl sulfide, Me2S. And what this is, this particular reagent is redox neutral. All right, if it's redox neutral, that means that any H's that were in the original alkene will still be there in the product. So on the left side of the molecule, we're going to have our double bond O. But because our terminal H had hydrogens on there, they're going to stay on there. So in this case, we're going to get formaldehyde. And the other two options are whether it's oxidative or reductive. So the oxidative conditions I gave you guys was peroxides. So, and typically with peroxide, you'll have hydroxide as well. And this is oxidative, so we put brackets with an O in it to imply oxidative. So what happens here is we get that. And then instead of having the H's here, we have OHs. But if you recall, this becomes CO2 plus H2O. That's carbonic acid. You probably learned that in your freshman chemistry class, that H2CO3 becomes H2O and CO2. That's that compound. This is H2CO3. All right, the other option was sodium borohydride, NaBH4. This is reductive. And essentially what happens here, it'll reduce all the carbonyls. We are going to cover redox in detail in this class again as well, if you guys did not cover it last semester. We will see it again. That's reductive. In short, when we talk about redox reactions in organic chemistry, we are referring to gaining or losing bonds to O. So if you see here that the bonds to O here are different from one to the next, so this would be redox neutral. Extra bonds to O is oxidative. Losing bonds to O is reductive. Okay, so we had a couple more reactions we did. We did a lot of reactions last semester, didn't we? Just getting warmed up. All right, so let's go ahead and start working on this side of this little flower diagram. So here I have an option for, say, an X on there. And then we had another option with an OH on there. These reactions, the conditions are similar. So the question I have for you guys here is, so it is going to be the addition of HX for both. Which one do you think requires concentrated HX? The alkyl halide product or the alcohol product? Got a 50-50 chance guessing right? So it turns out that if you specifically want the halide on there, they should be concentrated. Because if you think about it, if it's dilute, it has mostly water around. Water is going to be your nucleophile here. So dilute. So if it's concentrated, X can be your nucleophile that comes in and attacks. All right. So in certain compounds, you do have a situation where, because remember, this is a carbocation mechanism, so we have to have a situation of rearrangement products. If you wanted to avoid the rearrangement product, what was the alternative for this reaction? Yep, it was the oxymercuration demercuration. So this one here, it looks the same product here, but I do want to mention no rearrangements. So no rearrangements. And this was the oxymercuration demercuration. It was mercury acetate. So HgOAC2. And then we also need THF. And then you will have ROH. So notice how I put ROH. So if it's water, it'll give you the alcohol. If it's an alcohol in that reaction, you'll get an ether product. And so the first step is the oxymercuration. The second step is the demercuration. So this is oxymercuration. And how do we demercurate it? Yep, sodium borohydride, the same reagent we used earlier in the last reactions, NaBH4. All right, some more alternatives for this reaction here. So right here, this is oxymercuration, demercuration. Demercuration. So what if I want to get the other product here? So, oops, I want to put the OH over here. That was the borohydride reaction. And that was what was the name of that reaction? Hydroboration oxidation was the name of it. So this was a reaction with BH3 THF. So there's your hydroboration step. And what do we use for oxidation? H2O2. Let's make sure. Yep. And NaOH. So it's hydroboration is the first step. The second step is oxidation. Interestingly, this second reagent, we used it a couple times now, the H2O2 and NaOH, it's commonly sold commercially as OxyClean. That is your OxyClean, is H2O2 and hydroxide. So you guys probably put that in your, if you put it in your, either for laundry and cleaning and whatnot. All right, more alternatives here. So what if I want to put an X in the anti-mark position? Yep, that was HX in peroxides. So that's ROOR. Oop, I think I forgot to mention the words here of Markovnikov and anti-Markovnikov. Markovnikov is where you had the more substituted product, and anti-Markovnikov is less substituted. So let's say these are mark additions here, and then these two down here that we just did are anti-mark. All right, I think I got all the additions here, so let's zoom out a little so we can see it all at once. So there we go. So if you guys remembered all these, you are in a good spot. So it's a lot of reactions. Can't even fit it all on one view there. All right, there were some other miscellaneous reactions here that I did want to mention while we're here. We will cover them in detail later this semester, but I like to have them here just for synthesis problems. So just off to the side here, we had a couple other miscellaneous reactions. Let's just start a new page. So what if I want to convert an OH into a bromine? And I want to do this in one step. So depending on the alcohol, you could use just HBr, but I mentioned a different reagent. It was PBr3. Yeah, PBr3 is the main one here. PCLO, another one. So PBr3, and then the other option was to turn this to a Cl. Yep, thionyl chloride, SOCl2. This compound is called thionyl chloride. So the next question I have for you guys is, if the OH is on a chiral center, are you going to have inversion, retention, or both? So is it going to be inversion of stereochemistry? Are you going to retain your stereochemistry? Or are you going to get a racemic mixture? So it turns out this is actually an SN2 reaction. This will be an inversion. It's technically an SN2 intermediate step in there. So we're going to have inversion of ferrochem.
The HBr will be received, right? It's going to have oxidation of the OH.
Yeah, so if you're using HBr here, we will see this reaction probably likely on Thursday. That's an SN1 reaction, so you're going to have a racemic mixture. All right, we didn't quite cover all the addition reactions per se. So there were a couple miscellaneous reactions with additions for alkynes. So what if I want to stop this reaction at the alkene? Sorry, go ahead.
You said it was an SN2 reaction?
There's an SN2 intermediate step here. We will cover that reaction, don't worry. We'll do the mechanism this semester. All right, so there were a couple options for hydrogenating the alkynes. Excuse me. So if you want to get the alkane, it's your standard H2 palladium on carbon that we've seen before already today. The other option was when we want to get the trans or the cis products. So Linlar, I heard Linlar is used for the cis or trans product. It's used for the cis product. Linlars. And that's Linlar's catalyst. And you also require H2 here. What if you want the trans product? What do we use for that?
And sodium hydroxide.
Yep, so I gave you guys two options last semester. There was sodium and NH3. And the other option was, they're really similar, and this is actually the more commonly used way now, is lithium metal and ethylamine. They are very similar. Either one works fine. I've actually ran this reaction before myself, this one with sodium and ammonia. It's really cool. Apparently, you have to have liquid ammonia, and when you actually dissolve sodium metal into it, it turns like a vibrant blue color. I would never think sodium would be blue, but apparently when you dissolve it in ammonia, it turns a bright blue, like vibrant blue color. And then you drop your alkyne into it, and you get the trans product at the end. All right, there was another reaction. I don't remember if I even covered this with you guys or not. I don't think I did. I think we ran out of time. But this was a mercury sulfate. I know a couple of you guys came across this in your homework because I was asked about this during office hours. Essentially what happens here is you're going to get an enol from this. So you're going to get that product here, and then it quickly equilibrates to the corresponding ketone. Think about it. All right. And there's the crash course for 241. Oof. It's a lot.